All right, Casey,
Yes.
can you introduce yourself and explain to anyone who doesn't know who you are and what you do?
My name is Casey Klepp. I'm an arborist. I'm an author, and I wrote a podcast called Completely Arbitrary, and the book is called The Trees Around You.
I wish you had a copy that we could see right now.
Man, if only there was an option. Ta-da! This is The Trees Around You.
That that is awesome. I can't wait to get a copy of that
Thank you. I'm
signed.
pretty stoked about it. It's just out
Uh,
now for 9 days.
wow. And you're about to tour around with it, is that right?
Yeah, I've kind of been doing a little bit of a tour already. I got started in earnest on not on the 23rd, on the 3rd of October. I was at Powell's Books in Portland and did a little book signing, and then had a big conference for a bunch of arborists this weekend, or rather this week also. And yeah, then a couple weeks I'll be going to Orcas Island up in Seattle, or up outside Seattle, then Seattle itself, and then Spokane. I'll be doing some other conference and things. So I'm ideally going all over the place.
What's the like log line of this book? What's it about?
Yeah, it's a great question. So it is about how to identify common neighborhood trees in the Pacific Northwest, which is something that you would think has already been done, but it actually really hasn't. Because if you go to the bookstore and you buy a tree book that says trees of the Pacific Northwest, it's going to be all those native trees out in the forest. It doesn't actually cover, no one's really looked into what are the trees actually growing outside your front door, what's growing on your street, what's in the parks, what's in your backyard. So that's what this book is about. Covers every single possible tree that could be growing in your urban areas, in the places that people actually live. So you walk outside, what's that tree? That's in this book.
What do you know of the program that they have here in Portland where you can plant a tree or multiple trees on your property? Do you know about that?
Oh yeah, we have a bunch of different programs like that in Portland. One, you can work with Friends of Trees. That's our local beautiful nonprofit. They're doing a lot of great work on getting people to get investment into their trees. So it's not just the city saying thou shalt plant a tree. It's this group that says, hey, trees are cool. You should work with us and we'll help work with you to make sure you have the best tree. But the city of Portland also a couple of years ago instituted a really fun program called the Free Tree Giveaway. And they literally just give people free trees to plant in their yards and then help them with management, saying, hey, here's how much it needs to be watered for how long. Here's how deep to plant it. Here's how to mulch it. Here's all the small little things that anyone could ever think about in order to take care of their tree. And then they come and check in on it a couple years later to say, hey, how's things going? Is there something we can do to help out? Is there anything you need? Can we answer any questions? Can we do a little assessment on the tree to see how it's doing? That kind of thing. And that is,
That's cool.
yeah, it's beautiful. We also do street tree planting through the city of Portland as well, which is nice. And I should know another hat that I wear is I'm on the volunteer board for the city of Portland. It's their Urban Forestry Commission. So I'm kind of in the background helping to give advice to the city. So I am paying attention to all these little things that are happening all over the place, trying to make sure that the trees and the people and the government are all getting along as best as possible.
So I just talked to an arborist out in Austin,
Mhm.
and we were talking a bit about the canopy out there. And there's serious drought and a lot of heat. Obviously, it's just a different climate than
Oh, yeah.
here. And there was a discussion. She was saying that I don't know what the title of the person is, but whoever's in charge of like trying to determine what the canopy is going to look like
Mhm.
and how to address it, we were talking about, or she was talking about how there's like a discussion within the arborist community or maybe the tree loving community or just people of cities about planting like native trees
Yeah.
versus whatever
Mhm.
trees might be what they think might work best looking into the future.
Mhm.
Can you talk a little bit about that? Maybe since I was talking to her about Austin, maybe we could have that conversation about the Pacific Northwest.
Oh yeah, that's a great one for both of these places. So mainly there's kind of two different things going on with that. One is there is a movement over the last several decades about trying to plant native trees in our urban areas. So before this, most of the trees that we would plant out west would be trees from out east. It would be the trees from Europe or from the East Coast. Those are the trees that when we first, the United States of America, kind of when I say we, but also Europeans before that, whenever they were looking to plant a tree, they would plant the trees they knew. So they would bring their European species over to North America and they plant them here. Then when they went from the east, they would bring their native species from the East Coast over to the West and down in Texas over to California, up here in the Pacific Northwest. And
Mm,
they would do fine. But people are like, well, wait a second. We have all of our own native trees here. Why are we cutting down our native trees and then planting all these non native ornamental trees? And often the non native ornamental trees don't do as well because of lots of different bits and parts about the ecosystem, the climate, the soils, all these kinds of things that make a tree adapted to a certain place. Those are different if you move that tree around. So the idea is, well, let's plant native trees because they're already pretty established and pretty they know how to deal with our environmental stressors. They're already adapted. So on the other side of that is this idea in arboriculture called right tree for right place. And I
yeah.
usually add on to that for the right purpose because usually we're planting a tree for some given thing and it's a good thing to think about. But namely, the idea is you want to plant a tree that is adapted to the circumstances that also won't cause conflict with the infrastructure around it. So it's the classic thing, don't plant a 100-foot tall tree underneath 30-foot power lines. You know, you've always seen those with like
Right.
the U-shaped power line trees. So we want to avoid that. You know, you also want to avoid planting trees along the street that are going to completely destroy the sidewalk because they have really shallow roots or something like that. So there's the idea of right tree, right place, which kind of says, well, if it's not a native tree, that's not necessarily a bad thing. You can still plant a tree that is non-invasive, that's not going to cause any damage, that is well adapted to the climate, and that's still going to be an okay thing. So the idea is, um, you don't necessarily have to stick with your personal, your the one palette of wherever you live. You can plant a lot of different things, the right tool for the right job, kind of idea. But then all
Yeah.
this is layered on top of climate change, where we can say, well, yeah, we can look and see what it is right now, but this tree is going to live for 80, 100, 150 years. What is the climate going to be like? And can we potentially plant a tree that is going to be better adapted to what we think the future climate is going to be like in Austin, in Portland, in wherever you're at? Usually that's looking at things that grow in hotter, drier situations, but also can take the cool temperatures of the hot temperatures. So a lot of Mexican trees would be planted in South Texas. Also, you could imagine a lot of Californian trees get planted in Oregon, and then Oregon trees planted in Washington, so on and so forth.
A part of their the tree's migration.
Yeah, yeah. It's actually the term that people use is assisted migration, and it's kind of a bit of
Yeah.
a hot topic because that's like saying, well, we're pretty sure that the mountains up here are going to be like the mountains down there, so we're going to start planting those trees up here. And people are like, whoa, 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 whoa. We do not have that is not our forest. We do not want your California trees up in our Oregon forests. Our Oregon forest is
Yeah.
doing just fine. So in the urban
Sure.
areas, if we're dealing with trees around our landscapes, it's usually not that big of a deal. We're already planting a lot of species that are not native, like I said earlier. So usually you're like, man, let's just see what it's like and see if these trees that are adapted to lower latitudes, but often higher elevations. Let's see how those work up here.
In Austin, she was saying that they have this goal of having 50% canopy cover over Austin, which is
Whoa.
pretty mind blowing if
Yeah,
you
that's
think about
huge.
it. Yeah. Yeah, it's huge. And she was talking about the quality of life that changes when you've got, I mean, she gave so many reasons, just like health being better because you're by a tree, but
Yeah.
also like the cover, the canopy cover over the city and the value of bringing down temperatures and the health benefits of that. It seems like it might be like it's going to be similar but slightly different here. What can you say about just the trees that we plant here and the benefits that we get locally?
Yeah, that's a really good question. It mostly comes down to the climate and what trees will survive and do well. So up here in Oregon, in the west side where we're at, this is Portland, we grow a lot of really intense conifers. Those are the big Douglas firs and noble firs, pine trees that everyone expects out here in the west. but they tend to be really big, large growing trees that people tend to not really want next to their house. They also tend to be really tall growing trees that don't really have wide canopies. This is actually um, uh, a great comparison to a place like Austin, Texas, where you down there are famous for oak trees. You have these beautiful oaks that grow out and have really wide canopies. They're also evergreen, like our firs and trees up here. So when we're looking at trying to get a canopy coverage over a city, the Portland canopy goal, I believe, is something like 32 or 35%. And the
Hmm.
idea is, well, okay, how are we going to do that? Where are we going to plant these trees and who's going to maintain them? They're on private property over their own houses. Excuse me, if they're on public roads, if they're in parks, that kind of thing. There's going to be different management kind of departments that have to keep track of it. So
Sure.
in the city of Portland, we're trying to plant a lot of trees. We also have a lot of power lines, so we can't plant trees like our huge pines and firs that grow really tall. A lot of times we have to plant smaller, shorter trees that grow a little wider. We also can't really force people to plant a tree that could get 150 feet tall and could get 4 feet or 5 feet in diameter right next to their house when they have only a five
Right.
foot setback between the next property line, right? So
Right.
so a lot of times if we are trying to make our goal of density a reality, then that really doesn't always leave room for giant trees. So you often
Right.
get a mix of space for big trees, and then where you have space for smaller trees, you're going to plant those. But mostly the goal is to plant big, healthy trees that are going to grow as wide as possible, but not cause any big conflict with, like I said, power lines or being too low where cars are hitting them, things like that.
Yeah. Okay. Let's move east so we can cover more of the country.
Oh yeah, let's do it.
Okay, so I was recently out in Pennsylvania and we were working on a treehouse build out there. And this particular treehouse was built in a tulip tree. And no, I haven't been paying close attention to my trees throughout my life. And I'm trying to now. This is part of the journey that I'm on and the reason why I'm having this discussion and other discussions.
Yeah.
But the tulip tree was awesome. I grew up in LA and we used to camp under the redwood trees
Mhm.
heading north up into the Bay Area. And so I'm used to seeing big trees. Obviously, they're a little bit different, but these were cool. They feel like they're surrounded by each other. I'm impressed at how tall they were.
Yes.
Anyway, I'd like to talk about the tulip tree in three stages,
Mhm.
as I had mentioned. Sort of, well, I don't know what to call those stages, so maybe you could define them for me to start.
Mm. That's a great question. Honestly, I think you defined them pretty well because it's mostly just kind of your adolescence, your sapling, your young tree phase versus the middle age
Yep.
versus your big old aged
Yeah.
trees, right? So
Yeah.
the tulip poplar, in particular, you noted that it's one of the tall trees. It is, in fact,
Yeah.
the largest, the tallest growing tree east of the Mississippi. So it is the
Interesting.
redwood of the East for sure. Famously, they are very tall, straight growing trees. They're also what we call early succession trees, and that's kind of plays a little bit of the part with the size and the age of a tree. Are you familiar with succession at all in the ecological sense?
No. No, I'd like to hear about it.
Well, it is essentially the idea that there are phases in a forest that happen
Mhm.
after a disturbance. So let's say a fire comes through, kills every tree, and you just have this blank forest space. And let's assume for now that it is kind of out somewhere where there's no invasive species. So we're just going to assume that the trees and the forest around it will begin to rebuild itself. This is early succession. This is everything kind of starts back on this big cycle at 0, maybe at 12 o'clock. So as we're timing, or as our clock is going to the right, at maybe 1 or 2 o'clock, you start to get some shrubs. You start to get some really small trees that are just popping up, and you get a lot of herbs. So you get a lot of things that want to be in the bright sun and absolutely growing as fast as they can. Those early succession trees include the Liriodendron tulipifera. That's the scientific name for our tulip poplar. It literally means lily tree with tulip-like leaves. Or I'm sorry, tulip-like. It bears tulips. Tulipifera bearing tulips. So
Mm.
what it does is, or what early succession trees do, is they grow really fast. We kind of think of them as like the James Dean, where they live fast and die young. They are going to grow as fast as they can, get as big as they can, and take up as much space as they can. And the tulip tree, of course, does this in spades because it grows really quickly and straight up. And it tends to like
Yeah,
to grow in the kind of wetland areas, like down in areas that have a little bit of water at the base where they can really not have to deal with any drought stress. They're always going to have some access to some amount of water. They grow
yeah,
up and they start to produce these big, huge limbs and take up as much space as possible in their youth. And that is really the big thing that early succession and these small trees just growing, like I said, about 2 o'clock, they start to create a closed canopy forest of really dense trees growing right next to each other. And they'll shade out the lower shrubs, they'll shade out all the herbs, and they will soon grow shoulder to shoulder. And that is what we call canopy closure. And that's when you have seen probably if you walk through a Christmas tree farm, you'll be able to like walk through next to the trees. You have a tree on your left, you have a tree on your right, you can easily kind of navigate between them. Canopy closure is when those trees get big enough that their canopies close up and you can no longer just walk through. Now you have what people think of as a forest. So
sure.
that then begins the second middle phase that is essentially intense competition, where now the trees are shoulder to shoulder. They're growing really tall to help keep their competition at bay. Over the time, the bigger, better, faster trees are going to shade out all of their lower neighbors. As those lower neighbors get shaded out, they die. When they die, the big trees kind of take over their spaces, and that is what liriodendron does. It gets big and it grows fast. But as these other trees die in this middle phase, now we're going to maybe we're about at 4 or 5, going towards 6 o'clock. So we're like maybe halfway through. Or not 6 o'clock, but in our clock, our analog
Yeah,
clock
yeah.
scale here. So once we're at 6, you then start to see there's new trees that are coming up underneath. And these are the shade tolerant trees. These are the trees that are okay with having a little darker sunlight and growing underneath the shadow of these gigantic trees around you, around them. They would be like, say, oak trees and American beech trees. If we're out west, it's actually true firs and western red cedars and these trees that grow really slow, very patiently, just waiting for one of those larger trees to end up kicking the bucket. And then when that tree kicks the bucket, they're right there in the wings, ready to go and take up over that
Mm,
space. So that then is transitioning into our late succession. So that's where we're going from the 6 to the 7 to the 8. So now we're about the 45 mark on our clock. Once you get to that 45 mark, that's when all of these old tulip poplars have gotten huge over maybe 80 or 100 years. They're
yeah,
starting to break, they're starting to decay, they're starting to get wounds and having their bases fail because some decays come through or something like that. And then you have these larger oaks and maples, and specifically the sugar maple and beech trees taking over this other space. Now, the thing that you're in late succession is when you see these early succession trees get really big and just kind of be these old sentinels out in the forest with these other
yeah.
trees that have their ability to grow in the shade. Now, because they can grow in the shade, their seedlings will start the process over of growing in the shade of those older, later succession trees. Then you get this little miniature cycle of these late succession trees growing underneath these late succession trees because they're all able to grow in the light. Now the liriodendrons, the tulipiferas, no, the liriodendrons are now the liriodendrons are tulip trees. They're gone because there's no longer bright sunlight for them to grow in. So they're going to go find another disturbance and they're going to grow over there. If another big disturbance
Interesting.
comes through, they'll pop back into that space and that whole cycle starts again.
When the canopy's been there for a while and they feel like they need to grow new,
Hmm.
how do they start again?
In
So
terms
that's
of,
not from the yeah, from not the blank slate,
yeah,
but tree already exists, and now we're gonna start from a brand new one. What is that process?
yeah. So they are famous for putting out thousands upon thousands of seeds. And if you've ever seen their flowers, they look a lot like magnolias. They're actually in the magnolia family, which is Magnoliaceae. And they have this kind of cone shaped central part, and that is filled to the brim with seeds. And each one of those seeds is what we call a little samara. And it's maybe about an inch and a half or so long. And it's got a little hook at the end. So as it falls from the top of this tree, it'll kind of flutter around and sail like what you imagine the helicopters from maple trees do. Really similar biological process. That's actually one of the most common convergent evolutions in seeds and fruit is that little helicopter kind of thing where they just drop and flutter themselves, a little distance away. So one of these
Yeah.
old trees will put out thousands upon thousands of these seeds every single year. And if there
Yeah.
is a tree that's a little distance away that falls over for whatever reason, maybe um, it was blown over in a huge storm. Maybe it was struck by lightning and exploded. Maybe there was a little bit of decay that got in there decades and decades and decades ago, and it finally has eaten up enough wood that that tree can no longer hold itself up. A little breeze comes and knocks it over. Now you have this small opening in the canopy, basically the size of one tree, but that still could be 40 or 60 feet in diameter. That
Yeah.
now is this little pocket of sunshine that's coming down into the forest floor. It's right there where hopefully a couple of these seeds find themselves, and then they say, sweet, and then they burst up in a flurry of activity. And if you ever walk into a forest that is really dense, you can find these really easily because everywhere else would be really dark, not a whole lot of things, maybe some ferns on the ground, not a big understory. And then where there is this break in the canopy, you'll have shrubs and herbs and little trees growing. It will be this little pocket of life that you're like, what is happening right here? And if you look up, that's the only place that light is coming through. So they will
Yeah.
continue to do that. And in places that have a lot of disturbance, like where they grow, which is in these kind of flooded areas where you can often have rivers flood in the spring and the fall, that is when they will break down a bunch of old trees or wipe some of the lower canopy away. Then the tulip trees will be like, "Hey, yep, we've been here the whole time. We're growing up again. Hey," and then they just pop up on the side of the a river or a lake or something like that.
Okay, so when the seeds fall and
Yeah.
they're spinning, is the purpose of that to get caught by the wind to take it further so the seeds not dropping?
Yeah, that's generally the idea. So as the trees, they can grow up to like 192 feet tall. That's like the top one. So let's just say 150 feet would be a pretty decent sized tulip tree. Those seeds are growing up in the top of that canopy. So they're about
Okay.
150 feet up. So if they
Yeah.
fall over 1 foot per every foot they go down, they're now
Mhm.
150 feet away, which is a pretty good distance. And the main idea is,
Totally.
of course, they don't want to be competing with their own parents, but they also want to find new habitat so that they can grow where there's not other trees. So
Yeah.
that if a big wind gust comes through and they're not just falling normal, just straight gravity, then they're going to get pushed potentially hundreds of feet, especially if it's like a hurricane, which they grow in areas that get that kind of wind and those forces. They could easily travel hundreds and hundreds of feet whenever they are really caught by some intense wind.
So when those seeds land, can they hibernate, or is this like you gotta catch it at the right time?
Yeah, I would have to recall because it's been a while. We actually covered this tree on the podcast, but I think that was about 3 years ago. But I think
Yeah.
most of the time they would fall onto the ground and then they would sit there and then start growing the next spring. So they would hibernate just over that winter time. And a lot of trees do
Yeah.
that. We call it cold stratification, where if you take a
Okay.
seed and you just put it straight in the ground, it won't grow because the seed is adapted to know the conditions that it lives in. And it knows
Wow.
if I put out my little tiny seeds or my little tiny root, which is called a radical, but it's spelled with an LE at the end rather than an AL. The little radical
Mhm.
is the very first little root that comes down. The first little leaves are called the cotyledons. Those
Mhm.
first little leaves are really tender. So as they grow in the fall time, they're going to get hit with cold weather really quickly. You're
Mm.
probably going to die. So
Okay.
they sit there and the seeds know I'm going to wait for it to get really cold for a couple weeks. Once it gets really cold for a couple weeks, then the next time it gets really warm for a couple weeks, and not only really warm, it has to see a certain amount of light in a given day. Once those two things are matched up, certain temperature, certain amount of light per day, then the seed will say, go time, then they will put out their little roots, then they put out their little leaves. But they have figured out over millions of years of evolution exactly what conditions they need in order to grow and survive and not have to deal with a really cold wintertime right off the bat. So they'll usually do one round of cold and then start growing the next springtime.
Okay, 2 questions. One, the first is within from the seed, is the root coming out of a specific spot, or could it come out from any spot? So is there a top and bottom to the
Yeah,
seed? I'll start with that one.
that's a great question. There really is. So a seed is made up of kind of two main things. One is the actual germplasm. It's actually the embryos, the best term to think of, and I believe that's the technical term as well. But often in botany, we have two different terms for plants and one for other animals. But that little embryo
Yeah,
will be sitting there and it has a giant, huge amount of food on it. So every time we eat a seed, we nibble down on that. We are actually eating both of those things, but that food is the endosperm. And that little endosperm is essentially, I think it's endosperm. Yeah, I'm pretty positive. That little guy is actually the food, the lipids and the fats and the proteins that the seed is going to grow on. So, right from
hmm,
wherever that germ is, usually that's all in the same exact spot. So, all these things repeat over and over. They're very much the same, every seed kind of thing, just like any other embryo always has the same parts kind of all put together at the same rate, the same time, the same place. So, that little embryo will send out a root, but it doesn't necessarily matter if it's upside down or not, because genetically,
yeah,
that root is going to grow down no matter what. It's called gravitropism. And what gravitropism is it's essentially this response inside every individual cell that tells it which way to grow. So trees
yeah,
have phototropism, and all the leaves up above. If you ever planted a teeny tiny seed in a tray in your house, then as soon as it pops up, 2 days later, it's like leaning over towards the light at almost a 45-degree angle. That's phototropism. It's the same exact process where you have these little chemicals, these hormones called auxin in the leaves. If the auxin grows on one side, and it will, rather, I should say, the auxin will get concentrated on one side or the other based on where the light is, or with gravitropism, where the gravity is. So if gravity is pulling down, it will move auxin to the top side, and then the root will grow straight down. So if the
cool,
seed is any direction, gravity is always going to be pulling that same direction, and the little radical will always make the same choice because it is designed and it has all these self-organizing hormones and chemicals inside. It's a really fascinatingly complex little structure, but it is the same thing that every tree will do. So any tree that's leaning away on the edge of a forest is doing the same thing, but it's doing it on every twig, every leaf, every branch up at the top rather than just the roots on the bottom.
what are the resources for that you might point somebody in to learn more about is it the physics of the biology of a seed?
You know, there's actually a really good resource. It's called the Triumph of Seeds, and that is by Lars Hansen. It's by Thor Hansen. It is called The Triumph of Seeds. This is a wonderful book for exactly that. So he essentially goes through and talks all about how a seed works. What are all the individual parts and how do they evolve and how do we know all this? Why is it that seeds are why is it that plants that produce seeds dominate the entire world? Every plant, every big tree, everything that you see except for mosses and ferns, they all make seeds. So that's not how life started. Life started with the equisedum, our horsetails, and ferns and fungus, things that make spores. Spores are
Mm,
very different than seeds. So
mm.
what is it about the seed and how did that initial order of plants evolve and take over every terrestrial space on the planet? He talks all about that. It's a really good book. I highly recommend it.
That's awesome. Thank you for sharing that. I want to get to the next stage, but I think I have one other question, which is that seed,
Yeah.
if you could get it to like hover
Mm-hmm.
in space. It doesn't need to be in outer space, though that could be its own question because of gravity, and I'm sure that there's some questions around that, but I'm not sure we need to know that today. If you could get it to hover without the soil
Uh,
and it still had everything else it needed,
yeah.
what does it do? Which sort of leads into the question of then what is the soil's purpose? Following up with that.
Yeah, great. So the big, I think, two parts of that. One is the gravity part, where gravity is the ultimate thing that is telling the little radical, that new first little root, which way to grow. And
Right.
plants over time have generally said, I assume that the soil is down, so I'm going to grow down. And so far, they've been right
Right.
almost every single time. So
Yeah.
that's their response. But if there is no soil there, they just keep growing down. Gravity is still telling them what to do. But if they can't find any soil, then they are unfortunately out of luck and they'll probably end up dying because they need to
Okay.
get to water and they need to get to the dissolved nutrients that the water that are they need, and they need to get to the dissolved nutrients in the water that, of course, is filled up in the soil. The other thing is they need to get fungus. Most trees, certainly conifers, but a lot of the broadleaf trees, like the tulip poplar, they all have connections with different fungus and microbes in the soil. So fungus will dissolve these different nutrients and then send it to the roots of the trees. That is a huge, really popular thing for researchers to be looking at right now. How does that relationship really work? So, if there is a root that's growing down and it can't find the soil, then it's not going to be able to support itself and it's going to essentially eat and use all the material that it had in its seed. Thor Hansen, in his book, The Triumphant Seeds, describes a seed as the germ, like a little baby. So the lunch is what the seed really is. That's what we're eating, even, humans and all other animals. So as soon as
Okay.
that seed or that little baby plant, that embryo eats its whole lunch, if it can't find the
Yeah.
resources to sustain itself after that, then it dies. It's out of luck.
Yeah. Okay. Um, so yeah, what I was saying is I think we definitely need to do the other two parts, but it's so interesting because so much has to happen up front. And um I don't think I want to overlook where the nutrients are coming. And one of the things that I heard you say is, and you seem to be careful about how you said it, which is that the water is capturing the nutrients that are broken down within the soil.
Mhm.
So does that should that lead me to believe that the nutrients are coming through the water through the roots and not the soil per se?
Yes, it is the best way to describe it. So usually, and I can't think of really any situations where it's not the case, but you will always see that the roots of a tree are growing and absorbing the water and the nutrients in the soil. But they're doing it at such a level to where it's hard for us to understand, in that it's not that there's just kind of a pool of water and if you dissolve nutrients in it, the tree is going to be fine. It usually doesn't work that way. Their roots grow and interweave into the soil in order to hold themselves up. So it's a whole other process. But that's, essentially hydroponics. It's the soylent idea where you can take everything and just give all the nutrients in the water and call it good. So there's something more to the whole thing. The whole is greater than the sum of its parts when it comes to soil. So this water in the soil is at the teeny tiniest little pores in every single crack, every single teeny tiny little bit of a soil particle that has some amount of water locked into it. And the micro and macronutrients are inside that water. They're dissolved in
Yeah.
tiny little amounts. So the tree will suck up all of that water. Of course, it's getting the water, but it also gets all those little dissolved nutrients as well. So usually water is
Okay.
the most important thing for a tree growing.
Um, and mycelium, am I saying that right?
Oh yeah, that's it.
Mycelium?
Mycelia too. I think that's the classic oxen, kind of thing. There's just a weird
Yeah,
way for us to say more than one mycelium is mycelia,
yeah,
but we also use
okay.
mycelium as like a large kind of collective term.
Can you quickly explain what that is and if it exists if it needs to exist for every tree, or is it completely separate?
That's a great question. It is completely separate.
Yeah,
It's not always so cut and dry. It's a really good question. So mycelium is a fungus. It is the body of a fungus. Fungus are not things like trees or people where they have like kind of a single entity. Well, some trees also don't have that, but that's a whole other story for another time.
yeah,
So they're essentially these microscopic filaments that grow throughout the soil. A fungus does is it will put its stomach on the outside of its body and it will dissolve the things around it and they decompose it. They turn what used to be in the body of some other animal or plant or something else into usable nutrients for themselves. So they are kind of doing this recycling work and they have
yeah,
often created a mycorrhizal fungal connection with the roots of many different plants, but in particular trees, and in particular conifer trees. So conifers are the pines and cedars and fir trees, junipers, that kind of thing. Almost every single one has this mycelial connection with some fungal species. And what
yeah,
that does is essentially gives them the ability to go further and deeper, and they are now basically connected in a direct relationship, not just with the soil that has the things in it, but the things that create the soil and that create the decomposition that then makes all those locked up nutrients available again for future plants. So, or from other plants into the plant that's, attached to it. So what happens is some trees kind of just don't need it or they haven't focused on it, they haven't developed that symbiotic relationship. When they haven't developed that symbiotic relationship, they're just doing fine. They're just doing all the work themselves. Conifers,
yeah.
they can often grow in the hardest, most intense places. A lot of things like rhododendrons and blueberries and Pacific madrone out here and the one down in Texas, they have a really special kind of ericoid mycorrhizal fungi that they make these connections with. Now, some fungi don't make any connections with trees whatsoever. Some are generalists, well, they'll make connections with multiple different species of trees. And then some are very specialist where they will only create one connection with one species of tree or maybe only a handful of very closely related species. So,
Very
depending
cool.
on the situation, you can have different fungus growing with different trees and connecting, say, a birch tree with a Douglas fir tree or an alder tree with a fir of another species. And now you're getting these like cross species, in fact, cross like order connections with a fungus, which is also in and of itself a whole different kingdom than plants. So it's really just this
Yeah,
like fascinating symbiosis, but it makes some trees really, really effective competitors in places where other trees, if they just did it themselves, wouldn't be able to actually survive.
that's very cool. Okay. We've definitely nailed down the beginning stage of the tulip tree. So, can you describe, and you touched on it a little bit, but what are we going to call it? Like the youth of a tulip tree. And
Mhm.
I'd be interested, I think, in knowing like if you just got one and you planted it in a spot where it's wide open, there aren't other trees around really. What's the that is to say, like, not a ton of competition per se.
Yeah.
What does the growth look like once it sprouts? Did I use the
Yeah.
right word? Do you
Perfect.
sprout?
Oh, yeah.
Ah,
Well done.
thank you. Thank you.
Grows fast. That's their big thing. So, like I said, with them being these early succession trees, they are the James Dean of trees. They grow fast and die young. Now, I say die young, but we're still talking about trees. These can live over 200 years. So they are the trees that want to get in the ground and they use a lot of their budget, just like anything else. You have just like anything else, they have a budget of resources that they can take from. So some trees will grow really slowly, but they will be very decay resistant. So they add a lot of effort to keeping their wood and their defenses really
Mm,
high. Some trees are like, I'm just going to grow as quickly as I can. I'm going to put out as many seeds as possible, and I'm going to grow up and out way faster than everybody else. But if I get any amount of wounding or something, which is essentially for trees, just wound the bark. Underneath the bark is the living cambium layer. That's the vascular system of a tree. As soon as you wound
okay.
that, the tree does not grow new skin. It has to close over from old bark slowly but surely every single year. We call this process compartmentalization. So
Okay.
Tulip tree, it does not compartmentalize well. It does not put its efforts into decay resistance. It says, I'm not going to try to live forever. I'm just going to try to grow as fast as I can, reproduce as much as possible, and then if I keel over, whatever. That's kind of that's a strategy I chose. The alder
Kind of
about here.
sounds like the sounds a little bit like the Elon Musk of trees, not
Oh
the
yeah,
James Dean.
absolutely. Yeah, if Elon would die at 45, that is the trick. He would have it. Yeah. Oh man, yeah, he's doing his best to be an early succession tree, isn't he?
He's just like putting all the seed out,
Uh-huh.
trying to create as many trees as possible.
Yeah. Yeah, yeah. If only he had the genetic variability of a tree, would we assume that he'd be very successful? But it doesn't quite work that way for people. Most trees, their genomes are about 100 times the size of humans. So they essentially have 100 times more genetic material in their DNA that could be turned on or turned off or reused or turned into something else in case they need to adjust to some future stressor, which essentially means that they have already adapted to that stressor in the background. For instance, our tree has been around for millions and millions and millions of years. So we know that this species has got so much experience under its belt that
Yeah,
when it tries to do all these new seeds, most of those seeds are probably going to survive because they have the genetic ability to adapt exactly to whatever condition they are. Because remember, trees can't move. They can't say, oh, it's too hot. I got to go to where it's cooler. They have to figure out how to live right where they're at and adjust to those precise elements around them. So trees are, I think they have a one up on Elon Musk.
let's see. Having that much DNA just yeah, no, I think you described that. It just comes from being around for so long.
Hmm. True. But what these trees
Yeah,
are going to do, so they're going to grow really fast, as tall as they can. They end up getting really wide as well. So they put on a lot of growth rings. But those growth rings are not as decay resistant as an oak or a hickory or something like that. So in that very
okay.
first stage, let's say this is the first 10 or 20 years of its life, it's going to grow as straight as possible, as quickly as possible, straight up. Once it gets to kind of a nice dominant place in that canopy, because remember, there's a bunch of other trees doing the same thing all around, still trying to compete as much as possible. Once the tulip tree becomes the dominant dog in that forest, then it's just going to keep its foot on the gas pedal and just keep going. And so that is really the thing with ecological early succession trees is they're just like go get that space in the canopy and hold on to it as long as possible.
Yeah. I think I'll remember this question and I'll hold off for the third section. Is there I'm trying to think of if there's anything else. Let me just double check here. Okay, so yeah, actually, can you tell me a little bit more? You started to describe the bark, but I don't think I understand exactly what you mean by can you re-describe how it grows and
Yeah. Totally. So the way that trees work is actually somewhat interesting. If you're not, well, I think it's very interesting. What am I saying? It's fascinating. All get out. But the way that trees work is different than what a lot of people think. They are actually rebuilding themselves on top of their old infrastructure every single year. We, of course, know these as your rings around a tree. So the very first year, you have that first spurt of growth. Every year after that, a tree is putting on two layers underneath its bark on the outside of the wood that it creates. So the wood layer, rather the layer that's closest to the wood, is called the phloem. And the phloem is spelled Phloem. And that layer of wood is essentially the vascular system of a tree that takes all the stuff that's made up in the canopy, all of the sugars and starches that the leaves create, and it takes it down through the rest of the tree to all the branches, to the trunk, and to the roots. So you can think of that as it flows down. The phloem flows down the tree. Meanwhile, just on the outer side of that layer, and this is all a tiny little layer, it's maybe a few cells thick. That second layer on the outside is called the xylem. And xylem is on the inside. That is pre-wood. Those are the cells that xylem moves things up and down. So that moves water from the roots up to the rest of the tree. The phloem is the cells on the outside. That is where everything flows down. Then on the outside of that is the bark. The bark is dead. The wood on the inside is also functionally dead. It's inert. It's only alive for maybe 2 or 3, at most 4 or 5 years inside underneath that layer of xylem. So as a tree gets larger and larger, the innermost bits of wood, we call the heartwood, that wood basically is just a structure that this new layer of cells is built on every single year. So a tree has a
Okay.
biological imperative to continue to grow outwards. And the only real living sections are those cellular layers, the xylem and phloem, called the cambium layer. On the outside is the bark that's dead. On the inside is the wood that's also dead. So the tree gets wounded in, let's say someone comes through with a hatchet, just whaps off a bit of the bark. Once that bark is
Yeah.
gone, it is not like a wound on somebody else. So if I am riding a skateboard or something and I fall and I get a little bit of road rash, I fall on some pavement and I end up scraping up all my skin. You get a scab, but then your skin will rebuild a new section of skin. It actually produces new skin. Trees don't do that. They cannot grow new bark from where the old bark was killed and destroyed. Because remember, underneath all that wood is functionally dead. It's inert. So it can't just say, oh, great, I'm just going to build a new layer of wood on the outside or a new layer of cambium or something like that. They are now dead and not able to do anything. So the edges of that wound, the tree compartmentalizes off the wounded area from the living area. And there's a lot of little technical details that we can get into sometimes. Certainly, when we're talking about tree houses, the amount of wounds that happen based on the species and how long you want that tree house to live there, huge, huge thing to consider because every time you wound a tree, that is letting in a possibility for decay. So you want to make sure
Yeah.
that you wound it as little as possible and give the tree the best ability to compartmentalize around that wound to keep decay away and at bay. So you have a healthy tree with a healthy structure with a healthy, beautiful treehouse structure inside that tree as well.
Yeah.
So
Yeah.
for any other situation, tree gets nicked, it has to have the wound or the non-wounded wood on the outside, the non-wounded cambium layer, slowly grow out from the living sections like it does every year. It puts on a new ring. That new ring of
Yeah.
wood slowly but surely grows up and grows out until it's covered over the entire bit of the wound. As it grows over that wound, that compartmentalizes off and essentially closes it back up, doesn't let decay get into it. And there's a couple other chemical things that happen in the wood to keep different fungus from growing towards the middle of the tree, growing up the tree and growing down the tree and growing around the rings of the tree. And we call that compartmentalization in decay, and we call that compartmentalization of damage or decay in trees, and we call that CODIT, CODIT. That's the acronym.
Hmm. Cool.
Yeah.
So each year as the tree grows out, is it stretching the bark and the bark is then coming in? I mean, I assume that maybe it's pretty big each year for a tree like the tulip tree,
Yeah.
but yeah, how's that working?
You have that exactly right. Essentially, the tree is building a new cylinder inside of an old cylinder. So if you
Yeah.
are to look up the bark of a tulip tree, you'll notice A, it's very beautiful, but B, it's got all these ridges and furrows in it where it looks
Yeah.
like it's kind of getting pulled apart piece by piece by piece. And that's because you have a
Yeah.
cylinder that is, say, a foot in diameter. Then
Mhm.
underneath that, you have a whole new layer built on the old structure, on that old wood. So that new layer expands out, and you get these little teeny tiny tears because now you're going from a 12-inch diameter cylinder to a cylinder underneath that is maybe 12.5 inches in diameter. So now you're like, well,
Yeah.
the other one, the one on the outside, has to break a little bit. When it breaks a little
Yeah.
bit, the tree has just like this teeny tiny moment of being um, a little bit at bay for some fungus. And there's actually some canker diseases that take advantage of that. We call them target cankers or something like that. Bullseye cankers is what they're called. And that's because every single year when there's this little teeny tiny microscopic crack, they get back in there and they cause a little bit of necrosis. They kill some of the wound wood there, and then it does it again every single year. So it ends up creating this bullseye appearance. I have a quick side
Interesting.
note. So with our tree, there is a second little tiny layer of cambium that's entire job is just to produce the bark. Because every year as that bark, as the old bark gets ripped, remember it's also dead, so it's not going to rebuild itself. There's this layer underneath that says, great, here's our new layer of bark that is now 12.5 inches in diameter. It fits perfectly, wonderful. And it just redoes that every single year. So as you go from a 12-inch diameter to a 12.5 inch to 13 to 14 to 20 to 40-inch diameter, now you have essentially the very outside. You could almost just measure the tip of each one of those little ridges and furrows. And my guess is that you'll notice that it's probably about that same size. And people have done this with like painting a tree. So you paint a tree, say a Douglas fir or
Mm,
a tulip tree that has nice smooth bark when it's young, paint it with a red stripe. And then in 20 years and 5 years and 10 years, whatever you want to do, watch how that red stripe gets ripped apart and broken up. You could then go back and measure the width of the little tiny ridges with a little bit of red on them, and that will equal the same diameter as whatever that tree was when you first painted it that color. But now the tree is just
that makes sense.
expanding out. Yeah. So the cylinder inside the cylinder is the best way to think about it. And then think about it just ripping apart each little piece of that cylinder over time. And where that happens is kind of like a little bit random, but it also is extremely consistent across different species. So the bark of every species will look really consistent across all of the individuals in that population. So they kind of do it randomly, but they do it randomly in the same way, which is really interesting.
Yes. Yeah, yeah, yeah. You said that leaves are like capturing and creating sugars
Yeah.
and bringing it into the tree. And I think I often forget, like, or maybe I need to have that explained a little bit more to me. Like the purpose of the branches and the leaves of, we'll talk specifically of our tree, and the difference between the roots and what the roots are doing.
Yeah.
Can you explain that?
Yeah, for sure. So the roots are gathering water and nutrients. That's their primary thing in terms of the biology of the tree. They also, of course, live in the soil and keep the tree up. So the roots are
Yes.
doing like kind of two main parts: structural stability as well as giving the tree the water and nutrients that it needs. Trees are what we call autotrophs. Now, what that means is that they create their own food. So, from the water that they get, they will bring that all the way up into the leaves, and then the leaves will conduct photosynthesis. And photosynthesis is literal alchemy. They take literal air, carbon dioxide, into their leaves through these little teeny tiny pores called stomata. And then through photosynthesis, and this really complicated thing, they rip the carbon dioxide apart, release the oxygen, and then rip the water apart and add the CO2 or add the carbon to it, and they create a simple sugar. So their sugar is the same thing that we get in maple syrup, for example. Their sugars are starches and glucose. It's all of those simple sugars that you've ever heard of. They use that for food and then they use that for energy and building themselves. So really, trees can be thought of as just a bunch of sugar converted into wood and flowers and leaves and things like that. But up in the leaves, they are creating their own food literally out of thin air and sunshine. As long as they can get water and a couple nutrients, macronutrients, and things that actually get together and create the little molecules that physically are the parts that a tree is made of. You know, these are the potassiums and nitrogens of the world. Once they get this a couple right nutrients, they pull everything else out of the sky and then they create their own food and then they burn that own food. And that is why they are autotrophs. They create their own food. Whereas we humans and every other animal, we're heterotrophs. We can only eat other things that have already produced food.
So it's hard to get out of the human meat sack and think about this. Like
Mhm.
what when it's making the food, um, I assume it kind of needs to go everywhere, except maybe in the center where you're saying that it's not quite living,
Yeah.
it's just structure now. So how like, I think of having a stomach, like I eat, it goes down to my stomach and
Mhm.
then I make energy that way. So it's making its sugars there
Yeah.
and then pulling it through the branches and it's like flowing through like blood? How's that working?
Yeah. So that is the other job of that cambium layer that we were talking about earlier. So the cambium layer is the vascular system of the tree, and it is present underneath every single bit of bark from the base in the roots all the way up the stems, out every branch to every twig. And then it goes through the little tiny stems that connect to each leaf called the petiole. Then it is like little capillaries out into the leaf itself. So if you ever look at a leaf, you see all the veins on it. Those are the veins that are connected to capillaries that then go down to the petiole, go down to that leaf stem, into the twig. And then through those layers and specifically through the xylem, it takes those sugars that are dissolved in water and or the tree will put it through the rest of itself, I suppose. So that is
And
the vascular system right there.
how is that how did we discover that?
That's a great question. Really, I don't know, but I assume what happened is someone etched into a tree, and I know that people have done this for thousands of years. You could get sap from a tree. People found out about, say, maple syrup thousands upon thousands of years ago. They realized, well,
Yeah,
this tree gets kind of nicked or cut or gets damaged. It puts out all this really delicious tasting liquid that comes out of it. So we
yeah,
realized, well, we could maybe use that over time. We maybe went a little too far. Maybe someone said, "Oh, I'm going to take my hatchet and I'm just going to cut all the way around this tree." They cut all the way around the tree and then it died. So we slowly but surely
right.
learned, oh, I see. There's this layer that produces sap, an awful lot like blood, where if you cut someone's neck all the way around, they're going to die because they're no longer getting blood going where they have to go. Same thing with trees. If you go around and cut all of the bark and you sever the cambium layer between the upper tree and the roots in the lower tree,
Yeah.
that tree will die. We call that girdling.
I've seen there's a company called, like, Marshmallow Fest or something like that,
Marshmallow
that's
fest. Okay.
doing yeah, I'll need to look it up. They're doing, like, high-end LiDAR, around trees and then creating, like, 3D models that you can look at,
Yeah, yeah, yeah.
and they might be completely making them. I don't know. I have, like, a goal of eventually talking to one of them to figure out what they're doing, but I've been interested in knowing, like, physics is taking us to a place right now that's, like, unlocking consciousness,
Mhm.
and I feel like all the sciences are kind of headed in that direction. Uh, I think this thing interests me about like what tools we have to look deeper into trees. Not everybody needs this. Like plenty of people can just sit under the trees and be like, this is awesome. But there's some of us who are like, I want to see like how this is working. Anyway, I don't know that there's a question behind this other than like what are there any technologies that you know of right now that are like kind of blowing your mind when it comes to trees?
Ooh, that is really a good question. I don't know that there is any real technologies that are kind of blowing my mind, but it's more,
Yeah.
I think the big thing that continues to blow my mind is the scientific community focusing on cooperation between plants and ecosystems and seeing them more as
Yes.
larger, kind of almost super organisms, as opposed
Yeah.
to individuals focused on competition. So, to the end of physics, or to that end with physics, regarding the physics that you talked about, the the idea of consciousness is really curious in terms of humans and animals. And that is something that, of course, we, being conscious creatures, are really fascinated by. But we're very biased.
Mhm.
Our consciousness is interested in itself, you know? Whereas trees, they don't have the same kind of consciousness. And I will not go so far as to say they do not have consciousness. We just can't, we don't know. You can't go talk to a tree and say, do you not? We can't also fathom it because it's just a different fundamental kind of existence. And trees are best understood as modular beings, where each leaf, each cell, each collection of twigs, each twig, each branch is all kind of on its own. It's doing its own thing as a part of this large collection. I actually heard just this week a researcher described trees as collections of branches. It's not one tree, it's many different branches, each one doing its own thing. It just so happens they're all connected by this layer and they're all sort of working together. But if a branch falls over there on the other side of the tree, that branch really doesn't care. It's going to continue to grow and do its own thing. So every time
Mm,
a leaf makes certain amount of sugars and photosynthate, the product of photosynthesis, it will first feed itself. Then whatever's left over will move down to the next part. Then the twig there will feed itself, and everybody takes their bit, and any extra gets moved down. So trees, of course, are
mm,
making lots of extra to support the entire rest of the tree. And there's certain
yeah,
choices being made inside the tree. But how those choices are being made is a mystery. What exactly is causing a tree to decide what to do when? We can look on the outside and say, okay, we see that this tree is responding in this way to this environmental stressor or some other stimuli. We can go in and we can measure what hormone was there, what was this chemical that happened. But it's just like love. We can look into someone's brain and we can figure out what chemicals are happening when someone says I'm in love and when they see the person that they're in love with. But we can't really explain what that is and how those chemicals create this other action, this other reaction over here, right? So
yeah.
it's really similar in trees, but it's also so completely vastly different where we're now looking at this thing like, well, what if we take a step back and what if we actually acknowledge that there's our fungus living inside the leaves of trees? These are called endophytes. There are fungus that live inside the roots and on the outside of the roots. And there's all these other interactions that are happening that we are now just starting to kind of look at and kind of like open our eyes and be like, oh my God, this is way more complicated. And there is way more cooperation than we initially thought. We very much were capitalists thinking, oh, all these trees are definitely fighting it out and they're trying to be the best, the tallest, and they're competing for everything. It is not
Yeah.
the case. They can, and they certainly do, but they're not 100% on one side or the other in terms of that political spectrum, so to speak. There's way more cooperation in a forest than we are even really quite scratching the surface of right now.
Okay. We've covered a lot of the whole process of the growth of the tree, but we'll just call this side of the conversation maturity. So I guess let's just start by saying how large do the tulip trees grow and how old can they get?
Yeah, that is a great question. The base age, I would say, is early succession trees. Again, they're growing fast and they'll live as long as they can, but they're not expecting to be, the ancient Brassicone pines or something like that, or that are 5,000 years old. I don't think anyone has been measured more than about 200 or so years old, and the
Yeah.
tallest ones, the tallest, I think, is about 192 feet. So they haven't quite
Wow.
broke the 200 feet tall that we've measured recently, but
Yeah.
inevitably there's always going to be the trees that we cut down hundreds of years ago. There was always a bigger one out there, kind of thing. So
Okay. And go
Oh,
ahead.
well, I was going to say that they often will get a significant size in diameter with like diameters
Mm,
reaching well over 10 feet, like really big, big round trees. At least that's the alleged, but
wow.
certainly you can go out and find a 6 foot diameter tree. You and I could lay down in one of those tree stumps and have the tree completely envelop us.
Totally. What other life does a tulip tree support?
That's
I
a really good
assume
question.
like yeah, birds, bees,
Yeah.
fungi.
So there is a whole lot of stuff. The thing with old trees as they get to maturity is they tend to develop a very complex crown. So the young trees that we were talking about, they are really short most of the time until they get, a couple decades old, start getting some real height on them. But then they will start to lose bits and parts. So you get hit by a really intense storm one year and maybe one of your big branches falls off. Maybe you get a little too tall and you are now easily the tallest tree in the forest. When that happens to trees like the tulip poplar, it's not that they can't handle that because the way trees grow is every time they have a new year of growth, they respond to whatever happened before. So if they're constantly getting hit by wind from their right side, they build the structure of the canopy of their literal wood layers to be more adapted to that wind situation. We call that thigmomorphogenesis, which is a fabulous $10 word. So as this tree's growing up, it's maybe a little too tall over the top of the canopy. It doesn't actually have the protection of all the trees around it. The trees around this one tree are all kind of protecting themselves. They're bashing into each other. They also, ones take the brunt of the wind and the others get a little bit of a release or a little bit of a reprieve from it. But then if you're too tall,
Yeah.
maybe your top breaks off. So when your top breaks off, you then have new sprouts that come from right underneath that and they start to grow up and take over the rest of the canopy. So given decades and decades, you'll see tulip trees create these really intense, large branches from these large trees. Some of them will fall, and that creates little holes. Anytime a tree has its bark ripped off, that is an opportunity for decay to get in. When decay gets in, decay will often start to create little cavities inside the tree. Now, the tree, of course, is trying to compartmentalize that, like we talked about. It's trying to keep out as much decay as possible. It's also trying to build up strong wood around it because it knows that as it decays, it becomes a little weaker. But those
Yeah.
are the little hollows. Those are little places that animals live. That's where birds are going to be living. That's where ants or other kinds of insects, a lot of different beetles will crawl into these holes, and some of them will burrow in and go underneath the bark. When that happens, woodpeckers will come. If there's a little bit of decay, woodpeckers will create their little holes and they will live inside of that kind of decayed area in the trees. So
Mm.
as this crown gets older, it gets bashed and bruised and battered, and it creates a really complex, interesting canopy. The more complex the
Mm.
canopy, the more places there are for other things to live in. Because they get so wide and so large and so tall,
Yeah.
they can create decay cavities where bears can live. So it'd be a little bear den up in the an opening inside of a tree. But
Wow.
in the ground, you have fungus that are connected to it. You have fungus that live in the tree that will ultimately decay the tree. But the trees, like I said, they know it is happening. They're able to respond to it and live often for decades while the tree is actively getting eaten out by different decay and is getting hollowed out. The trees will be just fine because that living layer on the outside usually is not affected by decay. So
Interesting.
you can have birds of all different stripes living on the dead parts and foraging for different insects that are living on those dead parts. You can do the same thing for different animals like squirrels and, like I said, bears, raccoons, that kind of thing. Certainly all those southern species that live in the southeast, because this tree is pretty much only east of the Mississippi River and then down all the way through Florida. So about the highest you'd find is maybe Pennsylvania or so. And then everything is go whoosh, straight down.
What is this? Is it a hard wood? How do you describe the wood inside of it?
Yeah, it's not that hard. It's kind of a soft wood, more or less, but it's very straight and soft grain. So if you were to go and like carve into it, it would be really simple and easy to do. So
Yeah.
doesn't it's not very hot. It's not very dense. You can usually cut it and chop it pretty easily, and you can burn it, and it
Okay.
it'll give you fire, but it's not going to be like a Pacific madrone or an oak or something like that that will put out a lot of heat. So yeah, it's one of those
So
trees that you can use for lots of different purposes. If you were to remove one and turn its wood into some kind of product, it's not the primary tree for that kind of thing.
yeah, but the wood is so it's somehow strong yet soft. Is that right?
Yes, that is right. So trees, wood itself is really strong. I mean, it's what we obviously build houses out of. And these
Yeah.
trees are really the trick with wood is that it is flexible and it has two main parts to it. One is the lignin. Lignin you can think of as cement versus cellulose, which you can think of as, say, rebar in a rebar reinforced structure, where cement is pretty brittle, but it's really strong in compaction forces. Whereas tension, rebar is used really well in tension. So if you build a big building or a bridge or something like that, the tension strength, the tensile strength in the rebar helps it bend and sway without breaking, versus
Mm.
the lignin, the cement, helps it hold on to this huge load on top of it. All the branches, all the water, and all the wood in the cambium, all the wood itself, all the physical weight of a tree. It doesn't
Yeah.
bash down the rest. those two things combined make trees really strong, but also very flexible. And again, every time a tree is moving and flexing, any little teeny tiny micro tear in those fibers is measured and then responded to the next year. So they can have really light wood as long as it's flexible enough not to break. But the flexibility and strength of a tree of wood is already really high. So when I say it's kind of a soft wooded tree, that's really in comparison to other things, you know. It's not going to be steel by any means. And there's certainly much harder trees. But yeah, so it's a soft wood compared to something like an oak or a ponderosa pine or something.
Yeah. Okay. Let's treehouse real quick.
Oh yeah.
So, what is the difference between a branch falling off and it kind of healing itself
Yeah.
and you putting a hole into a tree? And when treehouse builders are putting what they call tabs in the tree attachment bolts, it tends to grow over the bolt and it'll just like keep going. And so the tree house builders like to say that the bolt actually becomes stronger because it's covering it completely and it tends to cover it more underneath, like it's supporting the weight of it. Could you just talk about maybe the difference between the two, if there is a difference or if they're the same thing, and then maybe we can just focus on what it's like for the bolt, for the tree and the bolt?
Yeah, definitely. So it is essentially the same process. The tree is responding to it in the same way as if a branch is broken off or pruned off. So that goes back to the same thing that we discussed earlier, the compartmentalization of decay or damage in trees. Code it. So what happens if you go out and prune a tree and you say, hey, there it is, you're going to cut the tree or cut off a branch of a tree. The tree responds to that in the same way that it would if it naturally broke, and that is putting up those different walls of decay resistance. Those are the chemical walls inside the tree, keep it from growing, keep decay specifically from growing into the tree, up and down the tree, or around the tree. And those are what we call the first three walls of response. Now, there's this fourth wall that comes into play, and that's the one that treehouse builders are mostly interested in. The others, of course, we're making sure that we don't want to put a bolt into a tree and then have that bolt start to grow a cavity of decay around it. It
Right.
happens. Certainly, we want to minimize it, but the way to minimize it is to drill that hole and put that bolt in immediately. Don't give it time for that fungus to really develop and let the tree do its work to chemically mark off and close off all of those things. Think about it like in the Titanic when there was it hit the iceberg and all of a sudden all this water starts to flow in. Well, those big doors they were closing, that they were like, close those doors, that's trying to compartmentalize off the water. Trees are doing that
Mhm.
exact same process, but you imagine the water as fungal pathogens trying to get in, and those doors as these chemical walls they're building. So on the outside, that fourth wall is called the response growth of the tree, and another term is callus wood. And that callus wood is that new layer of bark and wood that is produced next to the wound. So the cambium
Okay.
layers, if you drill a hole, let's say it's an inch in diameter, an inch and a half diameter hole, that hole is now an inch and a half diameter wound in that tree. There's no way around it.
Right.
As
Yeah.
that tree then responds, the living layers, and my hands are up like this. Imagine my fingers as the sides of that hole if we're looking at it kind of at the level of the bark. So my
Yep.
fingers are the living cambium layer. They will
Okay.
every year put new growth upwards, but now they've also compartmentalized and made this callus wound right next to where the hole itself is. So that
Got it.
wound, that callus section, will basically produce wood as well, but that goes every direction. So it goes not only up and away, kind of radially out as the tree grows and puts on new rings, but it will also do it over towards the hole as well. And as it grows towards the hole, it creates what we call ram's horns. And you might have seen this if you have ever cut into a tree and noticed this really strange pattern of wood. That's where there was a wound years and years ago. And then as it grows out, it creates these ram's horn like appearances where it looks like these kind of circular wooden waves that then crash and meet to each other. Then a new layer of wood grows on top. That is the full
Mm,
compartmentalization of that wound in the tree. So with the bolts,
mm.
what's happening is the tree is growing new wood towards the bolts, and then it's also putting new wood out away from them. And so as it grows out and away, that wood is just a little bit stronger and tougher than the normal wood because assumingly the tree's like, there is a hole here, there is a wound. So I need to put a little extra work into this wood. So it's a little extra strong because now it's going to be dealing with a section that's going to be a little weaker. So this works well for treehouse builders because now they can put that wound in on purpose and then have the tree's natural responses keep the decay out and then build a really strong bit of wood around that tab, around that bolt,
Yeah.
so that now it is holding it up even more because the tree is basically saying something's wrong. I'm going to respond to it by putting a little extra weight into this particular section. So it
Yeah.
does work out really well because then now the tree's compartmentalizing off decay and making the whole structure just a little bit stronger than what it would be otherwise.
Is there anything else? I mean, I'm new to the tree house building. I still haven't built one, but and I know that you have some experience at some conferences and
Mhm.
stuff, but I'm just curious if there's anything else that you can think of that might be interesting to tell me about the relationship between trees and a tree house or a tree house build.
Oh, yeah. Oh, there's lots of stuff. The biggest thing to think about is that you're dealing with a living being. You're dealing with a living organism that has
Hmm.
not grown up and developed with a treehouse in it, on it, around
Right.
it, right? So the two big things that I always think of that I always talk about whenever I think about tree houses and how to build them is one, don't forget that the tree is growing underground. It has roots in the ground. And if you are to bring in what it amounts to a construction site right underneath the tree, right on top of those roots, your really
Yeah.
big, beautiful, healthy tree could then get all the soil underneath compacted, could get roots damaged, lack of water, all these kinds of things that cause the tree a lot of stress in terms of its underground structures. That's, of course, the roots. They're doing the absorption of water and nutrients. If you damage those, now you're affecting the whole rest of the tree. I like to joke
Yeah.
that if you cut a tree off, oftentimes you could have a new tree sprout from the roots. So you can cut the head off of a tree, what we think of as the tree, and the tree will be just fine. But if you take
Yeah.
that top and you put it into the ground, a tree will not regrow roots. Most of them, at least. I think maybe the willows can be the only example, but you could take a big tree, like a 12, 24-inch tree, and you could cut it off and it will regrow itself, but the top will not regrow its roots. So when you think about like, okay, actually the most important part of a tree? It's really underground. So if you mess with that too much, then you are going to be building $1,000 structure, many thousands of dollars worth of structure into a ticking time bomb of something that might just die here pretty soon. So the first thing I always say is focus on your job site management, focus on keeping track of those roots and keep them as healthy and undisturbed as possible. The second
Yeah.
thing would be understanding that you are now putting a huge amount of weight in a tree that has not dealt with it before. Of course, you're also wounding it. So you want to take care of the tree as if you're building a really intense and expensive thing in a living organism that could die at any moment. So we know how to take care of trees. So we want to avoid doing something that's really going to harm us.
Sure.
Pruning a lot of the branches away, not always a good idea because that's how the tree
Yep.
makes its food. And if you can build a tree house kind of lower down on the tree so that you're not putting a huge amount of extra weight way up at the top where it's really moving around a lot, that'll be
Yeah.
another big help. And then realizing that this tree is going to continue to grow if we do everything right. So if you make a tree house that is, for all intents and purposes, a static thing in a living dynamic organism, now you're finding yourself creating a situation where there's going to be conflict in the future. So you have to make sure to think, okay, this tree is going to be moving. It's going to be swaying. It's going to be putting on new growth. It's going to be making itself a little bit bigger over here. Some of the branches up
Yeah.
above might fall in a big windstorm. So maybe prune it to make sure that you're taking out any damaging or decayed, any wounded things that are up at the top of the tree, but leave as much live canopy as possible. Minimize how many times you're drilling into the tree and causing those wounds so that the tree does not
Yeah.
have to deal with a whole bunch of things happening all at once. Then give it a little bit of grace to deal with that. So don't expect that the tree is going to be like, I'm totally fine next year. Give it
Yeah.
a second. It's like getting a tattoo. Your body just took a hit. Take it easy, drink some water, have a nice meal, and then just relax for a second.
Don't go swimming.
Don't go swimming, don't go drinking a bunch of booze. Yeah, so you want to make sure that the tree is well taken care of because you are putting a lot of your effort and a lot of your trust in that tree, and you, I
Yeah,
think, should really have that tree's trust as well. That tree should trust that you are not going to completely destroy it while you are
yeah,
augmenting its reality in a pretty intense way. So make sure to think about its needs so that it will come back and serve you guys and the treehouse as best as possible.
perfect. So I think I've asked this to everyone so far. Can you speak to the trees?
Can I speak to the
And
trees?
they respond.
Man, no, I don't think so. I can speak to them for sure. And do I often? Absolutely. I
Yeah.
love to talk to trees. Often I'm actually just talking out loud around trees. That actually happens
Yes.
pretty frequently.
Yeah.
But trees have a fabulous amount of dignity, and I don't think they are in any way really interested in humans. I think they're more like, I don't really want to talk to you. You guys have really not given me much in the last couple hundred years. And those who did, you've kind of just pushed off to the side. So I don't really care too much. I don't think that I have any expectation of trees talking to me because though I do love trees, I don't know that they will take me personally as like one that they would say, you know what, I am going to say something to that guy. So I think I have to leave them without the expectation that they need to stoop down to my level. They're above me in every possible way, and I'm okay with being
Yeah.
like, I'm just going to say this out loud. I hope you hear, but you don't need to respond. It's cool if not.
Do you have a tree that, like, when you think of from your youth that you'd like to share?
Ooh, honestly, I don't really know that I do. I have in the past. When I was a kid, I built 2 tree houses. One was in, what turned out to be like a neighbor's tree, but it was like the back 40. No one really cared. Like everyone was just kind of hanging out in that space. And I remember building a tree house, or actually, I think I was too young. So one was built more or less for me out there, but it was from like bits and parts of a remodeled tree. It was just like a whole staircase laid up onto a platform kind of thing. And I loved that. And I was so sad when they removed it. And now as an adult, I can think of, well, as an adult who is a now professional published author on tree identification, I can look back and
Yeah.
think, oh my God, that was a bird cherry. That's Prunus avium. I know exactly what that tree is, remembering the
Mm,
details of it now as an adult. Same thing
yeah.
for a maple tree that was in my backyard that I built myself with my help from my good friend Joey and a bunch of other friends way back in high school and middle school. We built tree houses in 2 Doug fir trees that I have in my mom's backyard. So
Wow.
those are the kinds of like relationships that I had, and I loved going camping. But it wasn't a particular tree. It's
Yeah.
more just being out there and being kind of with and around the plants and the trees that are the thing that I look on and think, man, yeah, okay, I totally did that way back when, but now I do it way more. I'm way more involved in trees than I ever was as a kid in a way that is more focused on the trees themselves rather than
Yeah,
just
for
going out
sure.
camping with my friends. And mostly it was me hanging out with my friends and having a campfire or something like that.
The end of this story might be interesting to just say, like, once you've got, and we'll use the tulip tree as an example, it's at the end of its life.
Hmm.
It falls over, and then what happens to it specifically?
Yeah, I think the end of life of a tree is it's a fascinating thing to think about because in terms of the tree itself, the tree might be dead. Sometimes it's not. If it's
Yes.
a tree like a willow, then it's going to fall over and usually sprout from the roots and continue on its journey. But for the tulip tree, living fast and dying young, it's going to grow up. It's going to get really big. It's going to get a little decay in it. It's going to fall over for whatever reason. Once it hits the ground, it starts the kind of big second phase of its existence. Being a tree that doesn't really focus on long term decay resistant wood or something like that, it's not a tree that you're going to see sitting there on the forest floor for a really long time. Certainly not compared to, say, a redwood or a western red cedar out here in the West. Those trees can lay there and not decay for literally decades or thousands or hundreds of years. Out there, in the native habitat for a tulip tree out east, those trees will grow really large, they will fall over, and then they will start to create a whole second ecosystem for a bunch of different animals. And this is a really important part of this story, I think, because that's the cyclical nature of life, is where once something dies, it then just becomes something else. So we would call it a what is the technical term? It's large woody debris. That would be the technical, forest term. But that really sanitizes the whole idea. It becomes
Mm,
a place filled to the brim with insects that will go into the newly dead bark, and it will eat that entire cambium layer right up. You'll find millions of little teeny tiny burrows underneath from insects, and these galleries are what we call them, right underneath the bark. Then you'll see some go into the wood. Then you'll see different fungus come up from the ground into the tree and start to decay it that way. You'll see things start to land on top of the bark and start to create a nice layer of duff or soil on top of it. On the edge next to it, you'll get salamanders that burrow under into the stem or into the trunk, the stump rather, at the base where that tree fell over. Then you'll have animals live underneath it. If it was hollow, they'll live inside of that hollow area. So they start to create their homes, and any insects that come inevitably become the prey for other animals on top of it. So you create this little tiny ecosystem of everything living and eating the things that are living inside of that tree. Years and years go by, it slowly decays and it turns itself into this kind of like mushy, big sponge of a piece of wood where much of the lignin may have been decayed already, but now you have just the cellulose strands and it's like a sponge filled with water. So as the soil around it gets filled up, as it decays and gets a little lower, you have this little bump in the soil. That little bump in the soil is like a big water balloon, and it will hold on to water for all the other plants and animals and trees around. Maybe not so much animals, but small animals for certain. Trees will send their roots under, and different herbs and shrubs in the same area will send their roots up through the soil and connect into this like sponge of water. And now you have this large tree that is creating a repository, reservoir for water for the rest of the forest as it's
mm,
slowly but surely decaying. Then on top of
mm.
that, everything is eating it, and fungus will take care of it. Things eat the fungus, and then you can get new trees growing on top of this very fertile area that the fungus has decayed the parts of the tree into now workable zones. It's giving it to all the other trees around as well, and then new trees will grow on top of it, and new trees will grow in the space that that tree used to have, probably a tulip
Right.
tree. So the cycle of forest succession starts over just the same again. So that is like part of the cycle. It's not linear. It's definitely not something that we can look at and say, here's the beginning, here's the end. Maybe for that one tree, we can say it has a life, or it's born, it goes through maturity and then dies. In the larger sense, it's just a part of a cycle that is repeating itself millions of times in every moment for every single little living thing in that whole ecosystem. So really,
Mm.
whenever a large tree dies and falls on the forest floor, it's just phase two of another decades long process that it's involved with.
That's so cool. Well, unless you have anything else to add, I think that was amazing. I learned a ton and I'd love to keep doing this with you. I feel like, I don't know, I'm working at a treehouse building company, but really what I'm trying to do is learn as much as I can about the trees, but also the community of people that
Mhm.
are also thinking about the life of trees. And I feel like a lot more is gonna come my way, like learning about the seeds and the birds and the whole ecosystem.
Yeah, yeah, definitely.
So being able to come back and check back in with you whenever whenever I need to would be awesome. But it was awesome, awesome, awesome having a conversation with you, Casey.
Yeah, thanks, Whit. I had a great time. So yeah, I would love to do this again. And the next time, if you were like, "Hey, I learned about this tree. I'm curious about these things," let me know, and then we can just chat and get straight into that. And then ideally,
We'll
I
do
won't
it.
have a head cold, so we can maybe do it in one place the next time. That would be nice.
I've got to up my game also, so we'll figure that out.
Okay, yeah, yeah, we'll be able to do it. But yeah, I think that'll be great. But yeah, the only plug I would say is have everyone buy the trees around you. Tell everyone to go get
Let's
that.
do it.
If they're in the Pacific Northwest, It's meant for you. It's meant for everyone in a city, wherever you live. If not, it'll be good for you. You can learn how to identify trees. I give a really great technique called the stepwise journey, which is basically, do you have any idea how to identify trees? No? Let me teach you from start to finish. And then you'll know everything you need to know about any tree, wherever you're at. So that would be the
I
only thing
love
I'd look
that.
for.
And are you gonna do the audiobook?
I would love to, but so far, no one has offered me the chance to do it. So maybe I'll reach out to the publisher and see. But the thing is, I can do the first, 70 pages or so. That's comparison, or that's the whole, how do you do it? What's this book about? What is this tree identification? Though, as soon as I start to talk about each profile of each tree, that's when there'd be way too much evangelism that would come into it. Because I had to really keep it short to fit everything on one page. So if I then can
Mm.
start to say, well, actually, let's talk about all these other things as well. That's when I think it'll be really fun. So each chapter would be pretty fun, I think, to do. So I think it would be a little
That's
bit
cool.
different as an audiobook. I think in a good positive way though. So I'll have to see.
Yeah, that's cool. Can't wait to see that.
Yeah. Yeah, but definitely no one else would do it unless it was like, I don't know, Liv Schreiber or some beautiful voiced celebrity. Then I would be stoked about it. But otherwise, no. Maybe I don't know. I'll have to think of some good options.
Well, when you see this, my buddy Craig, who I don't know, for lack of a better term, producing this show with, although it may be having conversations with, because we've just known each other since we were like 2 or 3 years old.
Mhm.
And the show is in a way based off of our conversations with each other about our own growing up and evolution and the direction we're headed. And I feel like trees are a good like through line for
Yeah,
us
okay.
to have a conversation about. But he is an opera singer
Yeah, yeah,
turning and over the last several years, he started doing, audiobooks and, other voiceover stuff,
yeah.
and he actually just finished writing a book also, and is going I think his goal is to now become a professor because he's trying to spend more time with his kids. And he's just constantly traveling around the world. He's literally finishing up at the Met right now and then headed down to Brazil for a performance down there. And then
Incredible.
I think he's making it back home right before Christmas. But he is a fantastic reader.
Yeah, 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 yeah.
So at some point you could do the two where it's a conversation. It could be like him reading the book and you interrupting
Yeah, I'm just gonna stop you
and
right
being
there.
like,
This tree
"Yeah,
sucks. You should
actually,
never plant it.
I'm glad I wrote that, but I'd like to say something about it."
That would be a hilarious take on my own book. Just break in like, well, he just can't keep quiet, can
Yeah. And he's just like, I mean, on top of it, we used to do improv together, and he's just like one of the quickest people I know. So it'd be hilarious. But
Yeah.
at some point, we'll have to have a conversation with him as well.
Yeah, yeah, we should meet up just to see what it's like. I don't wanna get my
Yeah.
voice, as a professional speaker, outdone, though. That's the problem.
He'll never let that happen.
Alright, thank God.
All right, Casey. Well, thanks again, and have an awesome rest of your day.
Yeah, you too, Whit. Thanks for doing this. I'll talk to you later, man.
Yeah.
See ya.
Bye.